Okay, so welcome everyone to today's 1W-MINDS seminar. Today it's my great pleasure to have Professor Alexandre to speak in our seminar. Professor Despremont is currently a full professor in the Department of Information at the CNRS Eco-Normal Superior. His research is broadly on optimization theory and algorithm with various applications in data science, machine learning, and statistics. He has received many awards and honors due to his great research contribution. He is currently serving on several editorial boards on several journals, including Mathematics of OR, SIME journals on optimization and mathematics data science, mathematical programming. So today he will talk about approximation bounds for sparse program. So Alex, now the stage is yours.
Thank you. Thank you very much for the invitation and the introduction. So yes, as you said, I'm going to talk about sparsity, feature selection, and the Shapley-Folkman theorem. And the talk will essentially be a mix of geometry, optimization, and statistics. So hopefully there will be a little bit for everyone. And I should really start by saying that this is joint work with Armin Ascari, who's a PhD student at UC Berkeley, and who is finishing this year, hint, hint. And Laurent Elgaoui, who's used to be at UC Berkeley, retired, and is now in Hanoi. And as well as Quentin Rebjoc, who's a PhD student at EPFL. So before we enter into the real action on the Shapley-Folkman theorem, let me start with a few basic reminders. So we're going to use a lot Minkowski sums, and the definition of a Minkowski sum of two sets is fairly simple. The Minkowski sums of the sets x and y is simply the set of vectors written x plus y, where x is in x and y is in y. And graphically, it looks like this. So if you have sets P and Q, their sum here, both triangles in this case, their sum is a polytope. And their Minkowski sum is a polytope. And well, one of the Minkowski sums have plenty of properties, but the one we really care about here is the one on the convex hull. So if you are given subsets Vi in d-dimensional space, the convex hull of the Minkowski sum of the Vi's is also the sum of the convex hulls of the Vi's. So convex hull and Minkowski sums commute. And keep that in mind because it's going to matter in what follows. So there's an interesting phenomenon about Minkowski sums and convexity that is fairly direct to illustrate graphically. So let me show you two examples that have been cooked up sort of manually. The first is regarding the L1 half ball. So this on the left is the L1 half ball. It's kind of obviously non-convex. And what happens is that we can take its Minkowski average. And what do I mean by that? Where we simply take the L1 half ball and take the convex hull of this L1 half ball with itself. Let's start by doing the average of two Minkowski balls, L1 half balls, sorry. And what we get is this set here. It's still non-convex, but you could argue that it's kind of less non-convex than the original one. And we can sort of push this procedure a little bit further. So this here is the Minkowski average of 10 L1 half balls. And you see that it's getting closer and closer to being convex. And in fact, when you push n towards infinity, you get closer and closer to this, which is the L1 ball, and that's convex, right? So that's one example. Another one, so here we're taking the average of a set with itself, but we're not limited to taking averages. But we can also take the sum of arbitrary sets. And in machine learning, it's kind of an age-old tradition to illustrate procedures like clustering, etc., with digits. So here we're going to use digits as a form of non-convex set. So here, these are not numbers. They're just point sets, and so they're sort of heavily non-convex. So 2 is kind of a non-convex set, and 3 also is kind of non-convex. What's important here is that they're approximately all on the same scale. And so we can look at what happens when we take the Minkowski sum of these 5 sets, right? And what happens is that you actually get this set on the right. because computing Minkowski sums is not entirely easy. This was obtained by sampling, and so it's a little bit blurry, right? And it's the border is kind of a mess. But this is part of the process, probably not part of the answer. But what's important about this Minkowski sum of these 5 completely arbitrary non-convex sets is that it looks very much like a convex set, right? It's close enough. And arithmetically, of course, it's kind of off the mark because 1 plus 2 plus 3 plus 4 plus 5 is not equal to 0. That we can all agree on. But here it's really this, you should read this geometrically, right? We have 5 highly non-convex sets and we take their Minkowski sum, and what we get is something that's quite convex, right? That's interesting. There's a sort of central limit theorem-like aspect to it. It kicks in very fast. So we are only taking 5 sets. They all look different, and yet what we get in the end is very close to being convex, right? So this is not something that starts at n equals 10,000. And so we can formalize this result a little bit. So the basic idea is that basically when you take the Minkowski average of a set with itself, basically the points can be written in this way. And this, when n goes to infinity, so the number of terms in the average goes to infinity, and the dimension remains fixed, of course, converges, and this will be made precise later, to the convex hull of the set C. That's important. And the same statement extends directly to some of different sets, arbitrary sets Ci. So again, the sum of the Ci's normalized by n converges towards the convex hull of the sum of the Ci's, which is also the sum of the convex hulls, right? So the main message here is that the Minkowski sum of sets converges to its convex hull. And in fact, this is a result that dates back from you can make this statement completely explicit, and it's a result that dates back from the 60s, and it's due to Shapley-Folkman, but they didn't sort of bother publishing it because the proof is fairly straightforward, and they sort of moved on to something else. And so the papers that actually produce the proof and publish the proof are due to Starr and Emerson and Greenleaf. But the result itself is really due to Shapley-Folkman. And what it says is that if you pick sets VI in RD, n of them, and you take a point in the convex hull of the Minkowski sum of these sets, which is also the sum of the convex hulls of the VIs, then you can represent that same point as the sum of n minus the number of terms in an index subset S points in the convex hulls of the VIs, plus a sum of S terms in VI. And I now realize that yesterday I thought there was a typo here, and n minus S should be here and S should be here, but it's actually the other way around, so my bad. You should never fix your slides last minute. So in fact, it should be S here and n minus S over here. And so the idea is that when D remains fixed, the number of terms in this subindex is limited to D, the dimension. What happens is that when D remains fixed and n goes to infinity, this here will dominate, right? Which means that X will not be too far away from being represented by the sum of the original VIs, not their convex hull. And the residual will be this term here, but there will only be at most D terms in this sum. And so as n goes to infinity and D remains fixed, the residual will become negligible compared to this term here, which means that the convex hull of the Minkowski sum of the VIs is going to get closer and closer to the original Minkowski sum, right? For this to work, you need the VIs to be roughly of the same scale, because if one of them dominates, of course, this is completely wasted. But otherwise, if they're roughly on the same scale, you get this sort of negligible part dominated by the controlled by the dimension. And so again, in an asymptotic regime where D is fixed and n goes to infinity, the Minkowski sum gets closer and closer to its convex hull. The proof is one slide, so let's do it. The proof is important because it tells you exactly what matters and what's happening here. So suppose X is in the convex hull of the Minkowski sum, right? One way to write this explicitly is to sort of expand the normalization constraints on the convex combination coefficients and write X and the representation constraint on X and the normalization constraints on the coefficients in one batch, and you get this representation. And this is shows that X, the vector X1, which is n plus D, has dimension n plus D, is a conic combination of vectors Vi, J, Ei, right? And if it's a conic representation, you can invoke the conic version of Karateodory's theorem to show that you can get another representation with at most n plus D non-zero coefficients, right? So lambda ij at most n plus d lambda ij's non-zero. And now you conclude by using a pigeonhole argument, right? The normalization constraints mean you at least need at least one non-zero lambda ij per set I, right? So you have n plus d non-zero lambda ij. You're going to allocate n of them at least to each set representation Vi. So these are the blue dots you see here. Now you're left with at most d non-zero lambda ij that you have to spread around n sets Vi, n representations Vi, conic representations. And what happens is that in the worst case scenario, they are uniformly spread over these sets n. And so you have one of them over d representations. But that means that for n minus d of these conic representations, the conic representation is trivial. And whenever the conic representation is trivial, it means that the corresponding point is in the original set, not its convex hull, right? And that's how you get the result I just cited before. So it's essentially a direct application of conic Karateodory, and that's the main sort of workhorse in the proof. So it's a direct consequence of Karateodory and this pigeonhole argument coming from the normalization constraints, right? And this also shows you that the bound is actually quite conservative, because it could very well happen that, as in this picture here, many of the coefficients get affected, the residual non-zero coefficients get affected to a single set or a few of them, and then you're doing much better than what the bound would predict. But the main message you would sort of you could remember from this slide is that, in fact, the number of non-zero coefficients, convex combination coefficients lambda ij, controls the gap between the Minkowski sum of the sets and its convex hull, right? So sparsity matters here. So that means that we can produce a more formal version of the results I just cited. And for example, say that if the sets Vi are uniformly bounded with the radius upper bounded by R, then the Hausdorff distance, for example, between the Minkowski average and its convex hull is bounded by R times the square root of the minimum of n and d divided by n. So you get this explicit convergence result. And this holds for the Hausdorff distance, but it also holds for a number of other non-convexity measures. And there are monotonicity results on the convergence, etc. And all of these are detailed in this great paper by Fradelizzi and others in 2017. So that's good to keep in mind. So that's it for the sort of geometrical part of the talk. So now we'll see that this result has direct applications in optimization. So I'll spend a little bit of time showing you how this Shapley-Folkman theorem allows you to write a priori bound on the convex relaxations of separable optimization problems. So let's start with sort of an initial problem structure that is specific in two ways. The first one is that the objective is separable, right? So the objective of the problem, the objective we are trying to minimize here is the sum of n terms fi of xi. So the objective itself is perfectly separable, but there are coupling constraints, ax smaller than b. And here, to keep things simple, we're going to assume that these coupling constraints are linear. And we'll see that we can extend that to separable constraints, but the linearity assumption makes the exposition a lot simpler, so I'm just going to start with that. And what's interesting about this problem here is that writing a convex relaxation for it by taking the dual twice is fairly automatic. And what you get as a relaxation of this original problem, so we make no assumptions on convexity of the affines. They can be arbitrarily non-convex for now. And what happens is that when you take the dual twice, what you get is, of course, a convex relaxation of the original primal. And this relaxation has a very nice structure because it's written as the sum of the convex envelopes of the functions fi with the same linear constraints. And that's true because the constraints are linear. It gets a bit trickier when they're not. Okay, but for us here, it's going to help keep things simple. Right, so that's our basic problem. And an important property of the convex envelope of a function f is that the epigraph of the convex envelope is the closure of the convex hull of the epigraph of the original function. And that has another important implication in our case. It means that the convex envelope and the original function match at extreme points of the epigraph of the convex envelope, right? So look at the epigraph as a set, right? And the epigraph of the original function and of its convex envelope have no reason to match in general. One contains the other. But at extreme points of the relaxation of the epigraph of the convex envelope of f star star, the two sets will match. So and so we'll see why this matters in one or two slides. So that's the first thing to keep in mind, first property to keep in mind. And second, we're going to define a quantity called the lack of convexity as a term rho of f. And that's just the maximum difference between f and its convex envelope. And if we take this highly classical example where we relax the indicator function by the absolute value on the interval -1, 1, the lack of convexity of this function, of the indicator function, is going to be equal to 1, right? So far, so good. So why am I talking so much about epigraphs? Well, what's important to realize here is that the epigraph of this separable problem has a very particular structure. And why does the epigraph matter? Well, it's because the convexity of the epigraph essentially tells you everything you need to know about the duality gap. And in particular, you can write the dual function as being computed by maximizing an affine form over the closure of the convex hull of the epigraph of the original problem, right? And this means, in particular, on the duality gap front, that if the closure of the convex hull of the epigraph of your problem is equal to the original epigraph, in other words, the original epigraph is convex, then you have zero duality gap. So that's what we care about. And why is this epigraph representation of the problem important in our case? but it turns out that when the problem has this specific separable format, the epigraph is a Minkowski sum of particular sets Fi. And the Fi's have this shape here. They are m+1 dimensional sets, where m is the number of constraints and is supposed to be fixed. And what the Shapley-Folkman theorem shows you in this particular case is that f star star of xi is going to be equal to f of xi at the optimum for all but at most m+1 terms in the objective. And this means that in an asymptotic regime where the number of terms in the sum in your original problem goes to infinity, but the number of constraints remains fixed, the difference between the epigraph of your problem and its convex hull, roughly speaking, becomes negligible, which means that the duality gap gets closer and closer to zero. So just to summarize what we've done so far in one or two sentences, if your problem is separable and the number of constraints remains fixed and the number of terms in the sum in the objective goes to infinity, duality gap will go to zero because the epigraph of your problem is a Minkowski sum of arbitrary non-convex sets of roughly the same scale, right? So that's good news. And we can make this result a bit more formal in a much more generic setting. So don't focus too much on the details, but I'll give you a rough flavor of this result, which is due to Alexandre and Temam which can be found in Alexandre and Temam in their 1999 book. It goes back earlier than this, but it's written in a very clean format over there. So let's study a much broader setting where we again minimize a separable objective function subject to separable constraints, and we introduce this perturbation term u, and so we define HP of u as the perturbed primal problem with parameter u. And this goes back to this sort of perturbation function definition of duality, etc., all of which can be found in Alexandre and Temam. It's kind of out of fashion now, but it's a very sort of elegant way of defining duality with conjugate functions, etc. So if you're curious, just take a look. But so again, this is our original problem. And what the result by Alexandre and Temam says is that suppose the functions fi and gij in your original problem satisfy some sort of mild technical assumptions, and define p bar of j as the product of m+1, where m is the number of constraints, times the maximum non-convexity of the functions gij. Then what you can show is that the optimal value of your problem taken at the perturbation parameter p bar. So that's a hard problem. It's something you don't have access to because it requires solving a non-convex problem. This optimum value is sandwiched between the optimum value of the convex relaxation of your problem at perturbation parameter p bar and the optimum value of the same relaxation at perturbation parameter 0, plus a gap term, which is again the product of m+1, the number of constraints plus 1, times the maximum non-convexity of the objective terms fi. So non-convexity plays a role in your a priori gap on the, a priori bound on the duality gap, and the number of constraints also plays a role. And again, what's happening here is that if the number of terms in your objective function n goes to infinity, this objective value is going to grow as well. And if the number of constraints remains fixed, in relative terms, this residual term or this gap bound will become negligible, which means that when n goes to infinity while the number of constraints remains fixed, the duality gap will go to 0. Okay. So that's a very nice result. It has a direct geometric interpretation. You can basically read the duality gap of the non-convexity of the epigraph, and you can control the non-convexity of the epigraph using Shapley-Folkman. That's the full story. And all of this requires one essential structural assumption or structural property of your problem. It needs to be separable. So now that we have this result, let's basically start to look for separable problems, interesting ones, where we can apply it and get a bounds on the relaxation performance. And one of the applications that actually turns out to be very useful and intriguing is feature selection. And so now we're going to switch to the slightly more statistical part of the talk with very familiar territory. Feature selection and compressed sensing, etc., used to be very active like 10 years ago. But the arguments were mostly based on restricted isometry properties, etc. And what we're going to do here is make a completely different set of assumptions using Shapley-Folkman to get a grip on approximation quality. So why do we care about feature selection from a purely statistical perspective? Well, the idea is simply to reduce the number of variables in your model while preserving classification performance in a classification task, for example. And the idea is that this has two major benefits. First, from a statistical perspective, it often improves test performance. That's counterintuitive in some way, because you have less variables to begin with. But in fact, what happens is that feature selection will remove useless variables, and these useless variables act as noise. So they have actually adding useless variables has a negative impact on test performance. And so if you can use feature selection to remove these, you actually benefit from a test error perspective. And second, and perhaps more importantly, feature selection helps in interpretation. So if you end up with 10 variables instead of 10,000, it's much easier to try to understand the basic mechanism behind your statistical results. And that's one of the main drivers behind all this work on feature selection. It helps you read exactly what's going on in a much more sort of human-friendly way. So this is, of course, an extremely popular and well-covered problem. The most famous instances of feature selection are probably lasso, L1 logistic regression, recursive feature elimination in using support vector machines, etc. The list goes on and on. It's very, very classical. And the reason why it's particularly effective in many areas is that usually the trade-off between sparsity on one side, so how big your model is, and statistical performance is very good. And so this is a sort of toy example I just worked out from gene expression data. So we're trying to discriminate between lung cancer cells and control. And we're sort of inferring a linear model and applying feature selection. And so the original model has a little bit more than 35,000 genes. And then we're going to shrink it to be expressed in terms of much fewer genes. And what you see is that initially, at least, when you keep the number of genes in your model above 5,000, for example, you don't lose that much expressive power and statistical performance. So from a statistical perspective, going down from 35,000 to 5,000 genes in your model is essentially harmless. And you can push things a lot further, in fact. So that's the first thing. Second is that what you care about is really the mechanism behind the distinction between cancer and control. And you want to narrow it down to a few genes. And this is exactly what feature selection allows you to do. It will also produce as a byproduct a list of genes that matter. And so this is the list in this particular case. Do not ask me for an interpretation. I don't have one. And don't try this at home. But this is the basic idea behind feature selection in practice. There's a very good trade-off usually between statistical performance and model sparsity, and feature selection allows you to exploit that. It's also used in imaging. So this is fMRI data. The idea is to localize your predictive model. So the idea, and that's a very common experiment where you place a subject in the massive fMRI machine, and then you ask the subject to perform a certain number of tasks, and you try then to use a linear model to discriminate between tasks using brain activity patterns. And of course, the idea of feature selection here is to localize brain activity to a limited number of regions in the brain so that you don't get a cloud of noise. And this is exactly what you see here on this image from the parietal team at INRIA, where in the lower right corner, they applied an L1 penalty to get a much more local version of the model, right? One important caveat is that feature selection inherently uses a polynomial number of sample points to test an exponentially large number of hypotheses, because you have to basically choose between n choose k support sets using what is usually a fairly limited number of samples. Which means that if you're testing an exponentially large number of hypotheses using a polynomially large number of samples, there's a very high potential for false discoveries. And indeed, when people started to get these huge fMRI machines, they got really excited and tested all sorts of things regarding brain activity. And this went a little bit too far, and the amount of false discoveries being published in this vein became quite out of control. And so some clever people, Bennett and others, did a very nice experiment to illustrate the fact that maybe there was a little bit of false discovery in this entire process. So what they did is that they took a frozen dead salmon and placed the salmon inside these fMRI machines. And then they asked the dead salmon to perform a certain number of tasks, right? And so they showed the dead salmon different images, and they asked if the dead salmon could discriminate between cats and dogs, for example, and then recorded the brain activity in the dead salmon. And sure enough, they found discriminative power in the dead salmon brain and were able to localize it in this image on the left. And of course, well, if this is not false discovery, then what is? Okay, so remember that again, from a statistical perspective, this feature selection problem is tricky because it's essentially requires you to test an exponentially large number of hypotheses using a usually fairly limited number of sample points. And this is a perfectly fun way of illustrating this issue. So why am I talking about feature selection here? Well, it turns out that many of the feature selection problems we care about fit in the problem format I just described. And I'm using one simple illustration here, which is multinomial naive Bayes. And so in the multinomial model, the conditional log likelihood looks like this. And so training your model by maximum likelihood basically amounts to solve this optimization problem. And the interesting feature of this optimization problem is that it's actually separable in the variables theta plus and theta minus. So here f plus and f minus are simply the sum of the positive and respectively negative feature vectors. And calibrating your naive Bayes model means solving this optimization problem. This has a closed form solution, but I'll come back and add a little bit of a twist to it later on. So first thing to notice is that maximum likelihood is a separable problem in this case, and that keyword should ring familiar now. Second thing to remember is that no one usually cares, but there is actually a linear classification rule behind the naive Bayes model, and it looks like this. And the vector in this linear model is a vector W, which is the difference between the log of the theta plus vector and the log of the theta minus variables, right? And so this means that if you want to perform feature selection in this naive Bayes model, what you need to do is to add a penalty on the difference of the vectors theta plus and theta minus. Whenever theta plus I and theta minus I are equal, the variable is not going to show up in your linear classification rule, and you can prune it out from your model, right? So penalizing the number of non-zero terms in this difference is going to perform feature selection in multinomial naive Bayes. And now the maximum likelihood problem you have to solve looks like this. And this has two important characteristics. The first one is that this is still separable, at least by 2 by 2 blocks, right? That's very important. We'll come back to that. Second, it's non-convex. And so the first question you might ask is, can you write down a convex relaxation? And the second one is this relaxation any good? So can you write down approximation bounds for this relaxation? And thankfully, the answer is yes, otherwise I'd be talking about something else. And we'll see how. So on the computational side and on the relaxation front, the good news is that the dual of this cardinality constrained naive Bayes maximum likelihood problem is very simple. It's a one-dimensional convex optimization problem in the variable alpha between 0 and 1, right? So what you're doing is minimizing the sum of the k largest coefficients of a vector h of alpha, which is produced using the positive and the negative feature vectors. So this is just a function of the single variable alpha. And overall, then, the optimization problem you get for the dual is this one-dimensional convex problem. And this is something, thankfully, we can solve very efficiently. It actually have you by bisection, for example, and the complexity is actually linear in the number of variables n, because it's equal to n plus k log k, where k is the cardinality target, right? Which means that solving the relaxation is not has roughly the same complexity as solving for the original model. So from a computational perspective, you get sparsity for free here, and that's important. So second, we have this relaxation, it can be solved very efficiently. Now the second question is, do you care about is the result any good? And that's where the fact that the problem itself is separable kicks in, right? I can rewrite my original optimization problem in this format, just transforming the L0 penalty to highlight the fact that the objective and the constraints are actually separable in the main problem variables Q and R. Okay, and if this problem is separable, I can directly apply the Temam and Alexandre result from 1999 to show that the optimum value from the original sparse multinomial naive Bayes problem, phi of k, is actually sandwiched between the optimum value of the convex relaxation of the maximum likelihood and the same optimum value, but for the target sparsity k minus 4. But you get this very nice and simple bound on the duality gap. The duality gap is bounded above by the difference between psi of k and psi of k minus 4. And that has a very nice statistical interpretation, in fact. So there's always this sort of hockey stick heuristic on getting to the right target cardinality. What this means in particular is that the duality gap is controlled by the rate of growth of the relaxation. And what this means in practice is that this rate is going to slow down when you start adding useless variables, right? Adding one useless variable is not going to improve statistical performance. And so that means that after you start adding useless variable, psi of k, the relaxation, will start to plateau. And when that happens, it means that the difference psi of k and psi k of k minus 4 is going to become small, which means that your duality gap is going to be small as well. And so the relaxation will be nearly tight. So what this bound tells you in particular is that the relaxation is tight as soon as you start adding useless variables, right? So I'll illustrate this graphically later on. What this result does not tell you is how to reconstruct a solution that actually satisfies these bounds. And unfortunately, this is not an entirely trivial result, and it takes a few pages. So I'll refer you to the paper for the primalization side. Just remember that it's possible. I'll give you a bit more details later on, but in the interest of time, I won't spend too much time on this. This result holds and is easy to explain for a multinomial naive Bayes, but it actually extends to a much broader class of problems that we call sparse programs, where you have where the objective is the sum of a low-rank term. So f is a loss function typically, and x of w is a linear model where x is a low-rank matrix, and the rank of x is bounded by R. And so the objective has this first loss in a low-rank setting, and an extra regularization term written gamma times the squared Euclidean norm of W. And in fact, gamma can be arbitrarily small here, and all the results that follow apply. And so you should take this extra regularization term as a mark of laziness. It's just that the results are much easier to extract when you have this regularization term, but it's from a sort of quantitative perspective, this does not matter too much. So here, just remember that you're solving for a sort of maximum likelihood problem, for example, in a setting where your underlying model is low rank. This works for constrained version, where you want the number of terms in the number of model parameters to be small and bounded by k. It also works in a penalized setting, where you penalize by the number of non-zero terms in W. So key examples of this problem structure is our lasso, which fits in this setting up to the regularization term, but again, this is sort of marginal, and L0 constrained logistic regression, the two of which are very, very, very widely used. And again, the main assumption we're making here that's particular to our setting is that the underlying model is low rank, which is kind of true for natural data sets in general. And here, the bidual of our original problem in the constrained setting, and the same similar result holds in the penalized setting, is this problem here, which has a convex formulation written D over here. And this turns out to be simply the interval relaxation of the L0 sparsity constraint. So taking the dual twice actually recovers a classical convex relaxation of the problem. And we can show this result. I'm going to try to, there's too much information on this slide, but I'm just going to summarize it for you very quickly. You can show that the optimum of the original problem is sandwiched between, sorry, in this case, it's in the opposite direction. The optimum solution of the relaxation is sandwiched between the optimum values of the original problem at k plus r plus 2 and the optimum value of the original problem at target cardinality k. And what you see here is a phenomenon similar to the one we observed before for multinomial naive Bayes, if R is small, the duality gap is bounded by the difference between these two terms. And again, if the growth of this function is not too fast, so if we're in a region where the number of variables in the target model is sufficiently large, okay, then the duality gap is small, because the difference between the left-hand side and the right-hand side is going to be small. And now that's the bound we get on the objective. And the good news is that if you want to recover a solution satisfying these bounds, all you need to do is solve an LP. In practice, you actually don't need to do it, because the LP is there to get you out of trouble when you are at pathological solutions, but you're never at pathological solutions in practice. And a very sort of simple primalization procedure works 99.99999% of the time. So just from a statistical perspective, why we are not talking about, I got bounds on, we got bounds on the duality gap without ever, for lasso, for example, without ever mentioning RIP. And the assumption we make here is completely different. We assume that the model is low rank. And what we get in return is a statement on the optimality of the objective function and on the objective value. What we don't get is a statement on support recovery. And it turns out that RIP-like conditions are necessary for support recovery. And so we get optimality in a certain sense, but we do not get optimality of the support. So that's an important distinction. If you want support recovery, of course, you need some RIP condition. But the good news is that the computational cost of the relaxation is comparable to the computational cost of the original optimization problem. So you get sparsity for free from a computational perspective. So let me finish by illustrating this in a number of simple numerical examples. The first one we used is an example on text data using very large scale. The point of feature selection is to start with large scale data sets because, hey, that's why you want to get rid of variables in the first place. And so we used data sets from Amazon, IMDb, Twitter, MPQA, and SST2. With sizes ranging from 30,000 or a few thousand to a few million features. And why would you use feature selection on text? Well, if you do text categorization, it turns out that feature selection will produce very nice topic models. So you do one category versus another, and feature selection will produce a bag of words very nicely representing a topic. So Laurent has worked extensively on this. It's very effective and very intuitive. So feature selection on a text data sets makes perfect sense as a way of isolating topics as a bag of words. And what we see here in practice is just the computational performance of a plain Python implementation of the dual relaxation and primalization procedure on a CPU. So this is the exact opposite of a deep learning experiment. It's a laptop with plain CPU and plain Python code, no optimization, and no nuclear power plant required to get your numerical results. And so and what you see is that basically from a numerical perspective, this is dirt cheap, meaning that feature selection dimension 12 million takes 12 seconds. And roughly speaking, the complexity is linear. And so you basically pay 1 second per million variables. Okay, so that's kind of cheap. And of course, all of this and our results are essentially impose a sort of trade-off between computational complexity of the feature selection procedure and statistical performance. And so the idea of this plot is to compare both of these for sparse multinomial naive Bayes, as it was detailed here, and a number of other classical feature selection techniques. So how do you compare statistical performance for feature selection? So the way we did it is that we first use one of these feature selection techniques to isolate a bag of relevant variables for our experiment. And then, so all the techniques for feature selection are different. But then once we have the selected variables, we use the same classification technique on these selected variables to get an idea of model performance. And we use the model performance after selection, so post-selection model performance, as our benchmark for feature selection performance. So essentially, the residual performance of the model after feature selection will tell you how good the feature selection procedure was in the first place. And this is what we plot here on the y-axis as accuracy. So this is the accuracy of the post-selection model. And in the x-axis, we post the training time. And so this is on the IMDb dataset. And what you see here is that there are a certain number of simple procedures that act element-wise, so they perform feature selection variable by variable. And of course, they are dirt cheap from a computational perspective, but they take a big hit in terms of model performance and accuracy. So they are over here in this region. There was a bug in this plot for the SVML1. It's not clear why, but we used sort of standard implementation. So I don't have details, but otherwise you see that all other feature selection techniques, so penalized linear models, sort of sit in this region where training time is in the hundreds of seconds and accuracy is in the sort of 85% range. And our results are somewhere in between. So what sparse multinomial naive Bayes does is get you roughly similar statistical performance in the 85% range, but it's 2 orders of magnitude faster than all the other penalized models, okay? And it has linear complexity. So again, rule of thumb, basic Python on a CPU, 1 second per million variables. We can also plot the duality gap bound for a certain number of these examples. So this is what I was sort of telling you by hand waving a few slides ago. The optimum value is sandwiched between psi of k and psi of k minus 4, these two shifted plots. And what happens is that as soon as the function value at the optimum plateaus, the difference between psi of k minus 4 and psi of k becomes negligible, and your relaxation becomes tighter and tighter. That's dimension 30 on the right, 3000 on the left. Sorry, 30 on the left, 3000 on the right. And in dimension 3000, of course, the difference between psi of k minus 4 and psi of k becomes completely negligible, sort of all over the place. And so your relaxation is essentially uniformly tight. Same thing for penalized, so essentially lasso and L0 logistic regression. It's the same plot, and you see that when the cardinality target k gets large, you again get this plateau phenomenon, and the relaxation is tight. Right, so that on the left, it's the duality gap plot for linear regression with an L0 penalty, so a lasso-like problem. On the right, it's the duality gap for L0 constrained logistic regression. And again, you see this very nice control on the duality gap. And now the duality gap, the difference is that there are 2 terms impacting the duality gap. K, the target cardinality, and typically whenever K is high, your duality gap is low. And R, the model rank. And whenever R is low, the duality gap is low. So low rank models in this case will have, for these relaxations, will have a low duality gap. So let me conclude by showing you a sort of plot of how well this scales with the number of features. And so these are experiments on, again, the IMDb dataset. And you can see that scaling is actually, in practice, sublinear. And finally, this is an experiment. Feature selection is, again, only really important when you have a large number of features. And so we took this classical conversion logs dataset from Criteo. It's 45 gigabytes. It has 45 million rows and 15,000 columns. So it's a feature selection problem in dimension 15,000. And we did this experiment again on a plain laptop. Of course, it's naively parallel, so you could speed up a lot of the pre-processing, but basically overall pre-processing, so handling nans, encoding categorical features, etc., takes 50 minutes for this dataset. Computing F plus and F minus, the sum of the positive and negative feature vectors, takes 20 minutes. And then computing the full curve below, so the full trade-off curve between number of features and a likelihood, which means solving 15,000 feature selection problems using our sparse multinomial naive Bayes relaxation, takes 2 minutes. Which means that here in practice, the computation complexity of the feature selection step itself is negligible compared to the pre-processing cost. Okay, so that's kind of nice. So just to conclude, Shapley-Folkman gives you a priori duality gap bounds for separable optimization problems that are fairly simple and explicit. And application into statistics and feature selection problems actually show duality gap bounds and optimality, make optimality statements using no restricted isometry property assumptions. Only the naive structure of the model assumption, essentially. And in the lasso case, a low rank hypothesis. And if you remember, one thing from this talk is that for naive Bayes, at least, you get sparsity almost for free, right? And you can control the duality gap, so you should do it, because in practice, this is always useful. And so if you're interested in reading more about all these results, and in particular about how primalization works, I'd refer you to these two archive papers, which were published also in AI Stats and are to appear in Simons. And we have code online to illustrate all the experiments I detailed before. And I'm done. Thank you again for your attention. And I'm happy to answer questions.